My name is Mariano Zeron, and in this video we're going to see how we deal with discontinuities and singularity points on functions that we want to approximate with Chebyshev objects. So the situation is as follows. What happens if we've got a function such as this one that I've got here? So notice that I've got two, let's call them special points in the domain where we want to approximate the function. So the domain where we want to approximate the function is this one here, from here all the way to here. But here we've got a jump, so we've got a discontinuity. And here we've got the singularity point. So this point where the function is not differentiable. So how do we deal with this particular case? Of course, this is not a situation that we will never encounter. There are some functions that we're interested in approximating with infinite pricing functions, which have these kind of points. They could be payment dates, they could be barriers, they could be strikes, things of this sort. Now, the good thing is, number one, we know where they are always. It's similar to this kind of situation. We know that it's going to be here, and we know that it's going to be there. It usually comes in the definition of the trade itself. Second, the remaining part of the function, that is this one here, that one here, and that one here, is analytic. So the main assumption that we make about the functions that we approximate, which is being analytic, still holds, let's say, by chunks. So in each of those chunks, you can apply all the theorems that we know, and we can apply, or we can build Chebyshev objects the way that we've been doing it for all the functions that so far have assumed are analytic. And that's the way to solve it, really, in the practical or in the context that we're interested in, is take the function, identify where the special or the pathological points are, and then subdivide the interval where we wanted the approximation into as many subintervals as you need. So here we would have this subinterval, here we have that subinterval, and here we've got that one. So we've got three of them. And in each of them, you can build a Chebyshev object that you know will have the exponential convergence and all the nice properties that we know of. This is something you can do yourself if you're implementing the whole theory into a library. But one of the things that we've done in our library is to manage this in a very easy way. So instead of having to build for this particular function 3 different objects that then you have to manage, what we have in the library is the possibility of passing a parameter where you specify where these points are. And internally, the building of the object will contain all the sub-objects that it needs to have, all the, let's say, chunks that it needs to manage independently of one another. And then when you want to evaluate a point, let's say you want to evaluate this point, then it will choose the right Chebyshev object in order to evaluate it. I really recommend that you take a look at one of the videos that we have on special points, which says exactly how an object with our library needs to be built if you want to specify these kind of points. Because it makes your life really easy. You don't have to be dealing with all the sort of chunks of the function, and then you have to approximate each of them with Chebyshev objects and so on. You end up with our library with only one object for the whole function, and internally it just manages everything in a very easy way for the user. So this is basically it. This is the way that we come up with, let's call them splines of Chebyshev, because you're building a Chebyshev object here, which is stuck or attached to the next one, which is then stuck and attached to the next one. This point you can forget about it. That point you can forget about it. You'll never face an infinite collection of these points. There's always going to be a finite collection of them. You can isolate them in this way, build the Chebyshev objects by chunks, and that's it. There's one last thing that I would like to mention. If you have a function that is analytic, which in principle you don't have to break up into bits, you can break it up and you may see an improvement. So a situation where you may be tempted to do this is, let's say, with Black-Scholes. I drew it in a way which I don't think illustrates the point really well. Let's say it's a Black-Scholes which is about to expire. What do we know about a function which is about to expire, a pricing function which is about to expire? We know that it's getting closer and closer to having a singularity point around its strike. And we know that singularity points are not good for Chebyshev. So what can we do in order to approximate this function that we know is analytic because it hasn't expired? So one of the possibilities is build a single Chebyshev object here. Let's say that you build it with 50 points, for argument's sake. and get really good degree of accuracy, 10 to the minus 6, 10 to the minus 7, something like that. The closer and closer it gets to expiring, the more that you'll probably have to increase the number of points. We still are within the analytic world, so we've got exponential convergence. We won't need to increase it by that much. But in some cases, it makes sense to break up the domain into chunks like this. So one here, one here. And in the same way as we did before, you end up with, if you use our library, a single object that internally has 3 objects. One for this chunk, one for that chunk, and one for that one over here. The reason why we do this, or why you would be perhaps tempted to do this, is because you're isolating the area of the function which is most difficult to approximate. By reducing the domain around that area, you know that you can approximate that part, which is a complicated one, with fewer points. This part is the function behaves in a very benign way, very few points. The same can be said about this part, very few points. And it can be the case, and in fact, in the video where I deal with special points in our library, I think I show it there, you can go from, let's say, 60 points at construction for the whole of the domain, down to roughly 30 points in total. Say that you've got 5 here, or 7 here, you've got 7 here, and the remaining roughly 15 go in the middle. But then that means you've got a 50% saving on construction or building of the object, which is always the slow part of the process. So every time that you can do this, or that you think that you're going to benefit by doing this, you can try it out. But of course, it's not something that you necessarily need to do, because the function is analytic. You know you could do away with 60 points, and off you go. It's just an option. On the other case, when you do have these jumps or these singularities, you really need to do it. But this is it for this video. It's a very easy idea, the one of breaking up the function into chunks. If you've got any questions regarding this or anything else, please get in contact with us. And otherwise, see you next time.